Hey folks, my name is Nathan Johnston, and welcome to Lecture 8 of Introductory Linear Algebra. Today we're going to learn about something called matrices, and there are a lot of different ways of thinking about matrices, but for now the way we're going to think about them is just sort of as a generalization of vectors. Remember, vectors, one way of thinking about them was just as a list of numbers, so sort of a set of numbers that was arranged in a one-dimensional fashion, just sort of along a line in a list. While matrices, one way of thinking about them is they're just a two-dimensional array of numbers. So some set of numbers that you arrange in a two-dimensional fashion, so like in a square or a rectangle. So let's just go through a couple examples of things that are and are not matrices to sort of get comfortable with the idea, okay? It's the type of thing that's best illustrated with some examples. So, for example, okay, if I arrange the four numbers 1, 3, -4, and 0 into sort of a 2x2 grid like this, that is a matrix, okay? That's an example of something that we would call a matrix. And just for the sake of sort of having consistent notation throughout this and future lectures, usually matrices will be denoted by uppercase block letters like this. So A usually refers to a matrix, just like lowercase bold letters usually refer to vectors, okay? It's just sort of the standard notation that we're going to use. Okay, well, what about this? I mean, the entries of a matrix, they don't have to be integers, okay? So, I mean, yeah, I might have 7 as one of the entries and -8, but then I can have pi as a number in a matrix, and 2.7, and 3/5, something like that. That's still a matrix. It also doesn't even have to be square, okay? So here, like, we've got sort of more columns than we have rows. Like, there's sort of 3 entries in the horizontal direction, but just 2 entries in the vertical direction. That's okay. It's still sort of a two-dimensional grid of numbers. It's still something that we call a matrix. Okay, for an example of something that is not a matrix, consider something like this. Okay, if I wrote down something like this, where I sort of have 3 entries on the top, but then only 2 entries on the bottom, that's not a matrix. Okay, so one thing that we do require is really that, like, there are well-defined columns and rows in the matrix. Okay, so here, I mean, I don't know, are they going like this, or like what's happening here? Like the numbers in the different rows don't line up with each other. That's not okay in a matrix. Okay, every row needs to have the same number of entries, every column needs to have the same number of entries as each other, and they need to sort of line up properly in a two-dimensional array. All right, and now so let's just go through some sort of terminology and notation just to make matrices a little bit easier to deal with and talk about. Okay, so when we talk about the size of a matrix, well, the size of a matrix is just a description of how many rows and columns it has. Okay, so for example, this matrix up here, this matrix A that we introduced, we would say that's 2 by 2. Okay, and what that means is it has 2 rows and 2 columns. Okay, and you can just see that from the matrix A there. Okay, B, this matrix B up here, that has 2 rows but 3 columns. So in this case, we would say that the matrix is 2 by 3, okay? It's always rows and then columns, rows by columns. Right, and of course, C doesn't have a size because it's not even a matrix in the first place, okay? So whenever we talk about, the size of a matrix, it's rows first, then columns. And actually, whenever we do sort of any discussions with matrices, it's going to follow that convention, okay? We're going to see lots of notation and different ways of talking about matrices, and you're always going to sort of want to distinguish the rows from the columns. It's always going to be rows first, then columns, okay? So keep that in mind. And, I mean, come up with a mnemonic or something like that to help you remember that. So, for example, I don't know if you want to think about RC Cola, right? Royal Crown Cola. I don't know if you guys have that cola anymore. Or a remote-controlled car, RC car. Just think of rows before columns. Something to help you remember that. Okay. Again, just a little bit more terminology to make matrices easier to think about and talk about. So if a matrix happens to have size 1 by n, then we call that a row vector, okay? And, sorry, I'm going to sort of jump around here, actually. A row vector, okay? A row vector because, well, it just looks like a single row, right? Here, this is a matrix that's 1 by 3. So that's a row vector. If it's 1 by n for any value of n, then that's a row vector because, well, it's just sort of a single row. On the other hand, if it's, m by 1, okay, so an example is like this one down here. If it has some number of rows, m, but then just a single column, then we call it a column vector. Okay, so this is an example of a 3 by 1 column vector because it just looks like a single column. Okay, and then on sort of the other extreme, if it has the same number of rows and columns, so if it's an n by n matrix, it has the same number of rows and columns, then we call it square. So for example, this matrix A that we saw way back up here, this is square because it's 2 by 2, right? There's the same number of rows and columns. So you can have 2 by 2 square matrices, 3 by 3 square matrices, 4 by 4, and so on. Okay, but this matrix B is not square. Okay. And oftentimes we want to talk about particular entries in a matrix as well, okay? And the way we do that is we use the same letter as the matrix itself, except we use the corresponding lowercase letter. So if we're talking about entries in the matrix big A, well, then we talk about the entries are a little a, and then the subscripts tell us what row and column we're looking in. Okay, so for example, I'm just going to introduce some matrix here. It's a 2 by 3 matrix, but it could be any size. So here's our matrix A. And then, well, the 1, 3 entry of this, so what we would denote by A1, 3, well, what this means is look in the first row, third column. Again, it's rows before columns, just like always. Okay, so rows before columns, so this means first row, third column, which is here, right? First row, then 1, 2, third column. So this is going to be minus 6. Okay, so A1, 3 for that matrix would be minus 6. If I want to talk about the 2, 2 entry, well, that's A2, 2, and that's the entry in the second row, so this row, and then the second column, this column. So it's going to be minus 4. All right, so that's just notation for talking about entries in particular locations in matrices. And yeah, I've already used this terminology. We use the terminology the ij entry of A when we mean aij. In other words, the entry in the ith row, jth column, no matter what I and j are. So this A13, we call that the 1, 3 entry. And that means first row, third column. Okay. Sometimes we're going to use slightly different notation for this, and we'll see an example of why we sometimes have to do this later on in this lecture. Okay. Sometimes we use this notation. This means the exact same thing. Okay. This big A with square brackets around it, and then ij means the exact same thing as little a ij. It just means the ij entry. It means the entry in the ith row, jth column. It's just sometimes one of the notations is more convenient than the other. So we have both of them. Okay. Usually we use the lowercase notation though, unless there's a good reason to do otherwise. All right, so yeah, I mean, a general matrix, if you throw all this together, then this means that a general matrix looks something like this. If it's an m by n matrix, so m rows, n columns, then we can write it down sort of like this, where, okay, A11, remember that means the entry in the top left entry, the 1, 1 entry, first row, first column. And then the entry in the first row, second column, yeah, that's A12, and so on. The first row, nth column is A1n. Second row, first column, that's A21, and so on. All of these are just sort of the notation that we just defined for this particular entry. So that's sort of one way of kind of explicitly writing down what a general matrix looks like. Okay, and we say that two matrices are equal if and only if they have all the same entries in all the same spots and they have the same size as each other. Okay, so really you need like every single aspect of two matrices to be the same for us to call them equals. Okay, so for example, I mean, this is kind of analogous to how with vectors, order matters, right? The vector 2, 3 is different from the vector 3, 2. Same thing with matrices. The exact positioning of the entries matters, right? So here are four matrices. We're going to just clarify exactly which of these matrices are equal to each other and which are not. Okay, so let's start off with this pair of matrices A and B. Okay, so A has the entries 1, 2, 3, 4, whereas B has the entries 1, 3, 2, 4. Okay, so it's the same entries, but they're not in the same spots, right? These 2 and 3s here, they swapped spots. So those matrices are not equal. For that reason, these off-diagonal entries here are not in the same spots. So those matrices are not equal to each other. All right, what about the matrices A and C? Okay, so in this case, yeah, we've got the same entries, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. The only difference is that the matrix C is a bit bigger. It has 3 columns, just with zeros padding out that third column. And for that reason, these matrices are also not equal to each other, okay? These matrices don't have the same size, so they have no chance of being equal to each other. You need them to have the same size. Padded zeros, they really do make it different, okay? It's not enough to make them the same. Right? And then lots of other pairs are not equal to each other for same or similar reasons, right? B and C not equal to each other. Oh, the entry up here is not the same as the entry up here, and so on. B does not equal D, C does not equal D. So you can check those on your own. There is one pair that's equal to each other, and it's just the obvious pair, right? A equals D, because, well, they're both 2 by 2 matrices, and then, well, the entries are 1, 2, 3, 4, 1, 2, 3, 4 in that order. Yeah, they're all in the same spot, so great. A equals D. And that's the only pair where equality happens in this example. All right. And then, well, one final piece of notation before we actually start doing things with matrices. The set of all matrices, the set of all m by n matrices, we denote it in this way by sort of a funky curly big M there, and then the subscripts tell us what size the matrices are. Okay, and if the matrices happen to be square, so same number of rows and columns, then we just sort of abbreviate the notation like this, big curly M with a subscript n. That just means they're the n by n matrices. So in other words, we abbreviate m nn as just mn, okay, if they happen to be square. Alrighty, fine. Let's finally start doing things with them, okay? And the first things that we're going to do with matrices are just sort of the naive and simple things, okay? So just like the first things we did with vectors, where we talked about how to add and scalar multiply them, well, those are also the first things that we're going to do with matrices, okay? And you can do them just entry-wise, the way you would expect, just sort of the same way that we did those operations with vectors. Okay, so addition and scalar multiplication for matrices, I'm not even going to read the definition. It's just saying, yeah, you do it entry-wise, you do it the way you would expect. So let's just do a couple quick examples of matrix addition and scalar multiplication. Okay, so let's just write down some matrices. These are not special matrices, I just made them up randomly. And we're going to do a couple of addition and scalar multiplication examples with them. Okay, so let's start off. Let's add A and B and see what we get. Okay, well, just by definition, the way you add two matrices is you just add them entry-wise, okay? So you just do 1 plus 3 in the top left entry. Great. And then 2 plus minus 4 in the top right entry. And then 3 plus 2 in the bottom left entry. And 4 plus pi in the bottom right entry. Okay, and then let's just simplify that down a little bit because we know what things like 1 plus 3 are. They're 4. Right, and then the top right entry simplifies to minus 2, and so on. Not much you can do in the bottom right entry. 4 plus pi just is 4 plus pi. You can't simplify that any, so you just leave it as it is. Okay, and that's what A plus B is. Okay, scalar multiplication is very similar. If I want to take this matrix C and multiply it by 2, so do the scalar multiplication with the number 2, well, the way you do that is you just do it entry-wise. Multiply every single entry of C by 2. Okay, so nothing fancy or surprising happens. 3 times 2, well, that's 6. 0 times 2 is still 0. 1 times 2 is 2. And similarly for the bottom row, just multiply every entry by 2. All right, there is one sort of hiccup that we have to make special note of, though. And to illustrate that, what if we tried to do A plus C? Okay, what if we tried to take this matrix A and add it to the matrix C? I mean, maybe there are a couple of ways that you're thinking of that can maybe make this work. Like maybe you just want to add the entries of A to the left 2 by 2 block of C or something like that. Don't do things like that, though. Okay, instead, if matrices have different sizes, right? A is 2 by 2, C is 2 by 3. If they have different sizes, we just say that sum does not exist. You cannot add them to each other. Okay, and this, again, this is very analogous to what it was for vectors, right? If you had vectors that had different numbers of entries, different dimensionality, you could not add them to each other. You need the same number of entries to be able to do vector addition. Same thing for matrices. You need same number of entries arranged in the same shape even, okay? So same number of rows and same number of columns to be able to do matrix addition. Otherwise, it just doesn't exist, okay? It's not a thing. Okay, if you want to subtract two matrices, again, nothing fancy happens, okay? We just define A minus B to be A plus minus 1 times B, right? And we can do this because we know what the sum of two matrices is now, and we know what minus 1 times a matrix is now. Okay, and again, like there's nothing fancy happening here, nothing surprising. This is just the matrix that you get if you subtract entry-wise, okay? If you sort of combine these two definitions together, addition and scalar multiplication like this, you'll just see that, yeah, okay, so the way to subtract matrices is you just take each entry of A and subtract off the corresponding entry of B. Okay, so for example, if we go back and use the same pair of matrices A and B that we had up here, so I'm just going to use these same matrices, but now instead of adding them, right, I added them before, now I'm going to subtract them. Okay, and if I subtract them, what do I get? Well, I mean, I get the exact same thing that I had up here when I did this addition computation, except now it's just a minus sign in between in every single case. So you just subtract entry-wise. And really, it's nothing surprising. It's just what you would do, even if I didn't tell you how to do it, right? This is what you would guess matrix subtraction is. Okay, so 1 minus 3, that's minus 2. 2 minus minus 4, be careful of your double negatives, that's 2 plus 4, which is 6. And then all the other entries are similar. And again, you can't really simplify the 4 minus pi. It just is what it is. All right, so I apologize. Today's kind of a dry lecture where we're just going through sort of definition and basic stuff. But it is important to go through this just to make sure that we're all on the same footing with matrices. All right, so the final thing that we're going to do for today's lecture is we're going to do what we always do when we introduce a new operation. And that is we're going to show what nice properties that operation has. Okay, so we introduced matrix addition and we introduced scalar multiplication for matrices. What properties do those two operations have? And again, there's nothing that's going to be surprising here because those operations are just defined entry-wise. Okay, so just like with the vector operations, vector addition and scalar multiplication, we got commutativity, we got associativity, we got distributivity, we got all these nice properties because those operations were just defined entry-wise, and all of those nice properties hold for real numbers. So we can just sort of apply the property to each entry in the vectors. Same thing is going to happen here. All these operations are going to have nice properties just because we're just doing them entry-wise. Okay, so for example, if I take two matrices and add them up, A plus B, well, I could have equivalently done B plus A. It doesn't matter. You're going to get the same thing. So yeah, matrix addition, it's commutative, right? That's that property that says, oh, you can do it in either order. It's also associative. You can group parentheses however you like. It's also distributive. So scalar multiplication, it sort of behaves well with matrix addition, right? You can sort of distribute the multiplication over the addition. It also distributes the other way if you have a sum of two scalars. And we also have this another nice property here that I don't know a name for that just says, well, if I do a scalar times A and then times another scalar, well, that's the same as if you just multiplied the scalars together ahead of time and then multiplied by A. So you can sort of do the scalar multiplication in either order. Okay, and again, none of these should be surprising. They're all from the corresponding properties of just real numbers themselves. But it is important just to write them down, mainly just to get you comfortable with how a proof of something like this would go, okay? And to get you thinking very carefully about what types of properties these operations have. Because in the very next lecture, lecture number 9, we're going to introduce an operation on matrices that's very not obvious, and it's not going to have some of these properties. So you're going to have to start being very careful very soon. All right, so how would we prove something like this? How would we show this? Well, we're going to go through a proof of property C here. We're going to go through this sort of first distributivity property. We're going to see where that comes from. And the way that you prove something like this is you just sort of work entry-wise, right? If we're claiming that this matrix equals this matrix, again, remember, what does that mean? Well, it means this matrix has the same size as this matrix, and it also has the same entries in all the same spots as this matrix on the right. Okay, so to show that they have the same size, there's not much we have to do, okay? The matrix on the left, because A, B, and C are all m by n, well, this matrix on the left is m by n, and this matrix on the right is m by n as well. Okay, so they have the same size, great. Okay, let's show that they have the same entries in the same spots as well, though. Okay, that's the other thing you have to do to show equality. So the way we're going to do this is we're just going to let I be some index. That's going to tell us what row we're currently working in. I don't care what it is, it's just some index of some row. So it can be any number between 1 and m. Okay, and similarly, j is going to be some index that tells me what column I'm working in. So it's some number between 1 and n, because there are n columns in these matrices. And then my goal is to show that the ij entry on the left equals the ij entry on the right. Okay, well, the ij entry on the left, the matrix on the left is C times A plus B. So the ij entry of it, remember this is one of those two notations that we introduced for the ij entry of whatever matrix is inside the square brackets there. So this means the ij entry of that matrix. Okay, and then you just start using definitions. Okay, so I've got a scalar multiple of a matrix. Well, by definition, scalar multiplication happens entry-wise. So this is the same as the scalar times the ij entry of A plus B. But matrix addition also happens entry-wise. So what is the ij entry of A plus B? Well, it's just the ij entry of A plus the ij entry of B. Okay, and now this is just a real number, so I can use properties of real numbers on it. C times real number plus real number, that's the same as C times first real number plus C times second real number. That's just a property of real numbers that we already know from earlier in our mathematical education. Great, that's sort of as far as we can simplify down from over here, okay? So I've taken the ij entry of the left-hand side and simplified it as much as I can. Now I'm going to do the same thing on the right-hand side. I'm going to take the ij entry of this right-hand side and simplify it down as much as I can. Okay, so the ij entry of this right-hand side matrix, CA plus CB, is, well, again, like this is matrix addition here, and the way matrix addition is defined is entry-wise. Okay, so we're going to just do, that's just the same as the ij entry of the first matrix plus the ij entry of the second matrix, and that's what I've written down on the right here. Okay, and now I've got two scalar multiplications, right? Here's a scalar multiplication. What is the ij entry of C times A? Well, again, scalar multiplication works entry-wise, so this is the same as C times the ij entry of A. Okay, and similarly, over here on the right, this is C times the ij entry of B. Okay, so after I simplify the ij entry of the right-hand side matrix as much as possible, I get this expression here. And again, this is just some real number. But now what I do is I stare at these two expressions here really, really hard, and I notice, oh, those are the same thing, right? CAIJ plus CBIJ, CAIJ plus CBIJ. They're the same number, okay? So they're equal to each other. So great, that's all we wanted to show. Right, now we've shown that the ij entry over here is the ij entry over there. They're the same thing, so great. All of those ij entries are the same as each other because nothing that we did here was specific to a particular value of I and j, right? This worked no matter what I was and no matter what j was. So every single entry of those matrices are the same as each other. So the matrices are the same as each other. C times A plus B equals CA plus CB. Okay, and that's all there is to it. So it's actually very analogous to how we prove these nice properties of vector addition and vector scalar multiplication. It's just you work with the entries and show all the entries are the same. Okay, so what we did today was we sort of gave the algebraic introduction to matrices. And remember I've said that everything we do in linear algebra is going to have an algebraic version and a geometric version, okay? And matrices, they are very, very geometric as well. We're going to see a geometric way of thinking about matrices shortly, but that's going to be week 4's material, okay? So for today and for the rest of week 3's material, we're just going to deal with matrices algebraically and try to get comfortable with actually doing computations with them. And then we'll see sort of geometrically what they're doing next week. All right, so I'll see you next lecture when we go over a couple other things that you can do with matrices, a couple of their other basic operations, and then we'll see sort of the geometric motivation for all of these things in week 4. So I'll see you soon for all of that.